All right. Okay, we're going to begin in chapter 5. And this is all about probability. Okay? And so we use probability as a tool to model randomness. Okay? And so today's class will focus on learning the rules of probability as we try to model randomness, okay? And randomness, if we think about it, can be said to be the source of variation, okay? Or is one of the sources of variation. It says randomness, yes, randomness is a source of variation. Okay, so, yeah, what does it mean to be random, okay? Okay. And so in statistics, we give randomness, or the idea of being random, a specific definition, okay? In statistics, random should mean that the outcome of a random event is uncertain, okay, and that and should not produce predictable patterns. Okay. On the other hand, random does not mean that we cannot model it or that we cannot understand it. Okay, so even if something is random, we can still model it and understand it. So I'll write this. Okay, so for example, the outcome of a coin flip can be considered random. Okay, which means we cannot predict the outcome of any given coin flip. Okay. Okay, and a series of coin flips should not produce any kind of pattern, okay? You might get a whole bunch of heads in a row, you might get a whole bunch of tails in a row, but overall, you should not see any kind of pattern in the coin flips. Okay. On the other hand, we can definitely understand the probability of a coin flip, okay? I think we all have this notion that heads has a 50% chance or 50% probability of appearing, okay? Okay, so we can say that a coin has probability of landing heads equal to 1/2, 0.5. Okay? Or in shorthand, we can write something like this. The probability of heads is equal to 0.5. Okay? And a lot of times I stick this R in there. It's not necessarily, it's optional. So you might also see probability that coin lands heads written this way. Just as a P or a PR, they're essentially the same thing, okay? So I think our textbook uses this, but if you pick up another textbook, they might throw in the R there. It's quite varied, but it's not a big deal. Okay, is that all right? All right, and then, and so we can, using computers or random digits, we can simulate the outcome of a coin flip, all right? And we want to draw a distinction between what we call empirical probabilities and theoretic probabilities. Okay, empirical probabilities, these are based on observed outcome, or observed, outcomes, or, evidence-based. Okay, so that's what empirical means. And so the idea here is, let's say you are from another planet or something. You've never seen a coin before in your life, okay? And you don't know how physics works, but you've got a good sense of, I don't know, I guess probability or things like that. But so you want to know, well, what does it mean for a coin, how often does a coin land heads? You have no idea how this thing works. So you say, well, I'm going to just try this out. I'm going to flip it, okay, and see what happens. So maybe after one flip, okay, it has landed heads, okay? So far, the observed ratio of heads to flips is 1-to-1. It's 100%, okay? But that would not be a good thing. So I mean, a good way to test this out. So maybe you flip the coin 100 times, okay? And after 100 coin flips, it has landed heads 47 times out of 100, okay? And so your proportion of coin flips that has landed heads would be 0.47, okay? And so you can take that and say, this is my empirical probability. The empirical probability that the coin lands heads is 0.47, okay? Meaning when I actually flip the coin 100 times, it has landed heads 47 times. So far, my understanding of this coin tells me that the next time I flip a coin, the probability that it lands heads is somewhere around 0.47. Okay, and that's the notion behind empirical probabilities. This is often used when the math behind calculating an actual probability, like a theoretic probability, is far too complicated. Okay, so a lot of times people will run complicated simulations to try to understand a possible outcome. So and this is often used in sports. Okay, we don't have math formulas to say, we predict that the Super Bowl winner is going to be, Carolina or whatever. Okay, we don't have mathematical formulas, but we can create kind of computer simulations, right? You have, on your own. At home, you can have an Xbox and have the computer play against itself and see what happens, okay? And, major companies like ESPN, they have more sophisticated ways to simulate these things, and they just run, a simulated game hundreds of times over, and they say, oh, in our simulated games, this is the outcome that happened. And so based on our simulations, we predict this team has this probability of winning, okay? It's not that there's some magic formula that they plug in the quarterback's height and weight or something like, they don't have stuff like that, but they run simulations and they get empirical probabilities. And so when you go on, different websites about sports, it'll often say these are our predictions, and those are based on simulations, okay? So empirical probabilities are based on observed outcomes or outcomes of simulations. Okay, they can be used to get a sense of what the theoretic probability is. Okay, so a silly example. Okay, so the silly example is you have never seen a coin before. And have no idea So you flip it 100 times, it lands heads 47 times. Okay, so your observed empirical probability is 47 divided by 100, or equal to 0.47. This tells us next coin flip. Should have a probability of landing heads something near 0.47. Okay? So this method is often used for complicated systems. Okay. Yeah, I think that would be actually a kind of a neat experiment, is if everybody had some kind of video game system and we just had everybody simulate a whole bunch of football games to try to predict, you know, Super Bowl outcomes or things like that. All right, so this is that's empirical probabilities. Okay, we're not really going to cover building simulations or anything like that. Okay, but this I do have to mention that this exists. Okay, because it is an important, plays an important part in modern probability and modern statistical modeling. Okay, the rest of this class is going to focus on theoretic probabilities, which is kind of our classical approach to probability. And we're going to learn the rules behind theoretic probabilities. Let me just see if I can flip to the next slide. Okay. So on the other hand, we have theoretic probabilities, which are, you know, these probabilities mathematical rules. Okay, this is the classical approach. Okay. All right, and so, you know, our class is going to focus on learning these probability rules. Okay. All right, so first of all, we have to kind of define this concept of an event. Okay, an event is when something happens, right? Okay, and we'll often assign letters or short words or names to an event. Okay, so assign a word or letter to an event. So for example, we can say heads is the event that a coin flip lands on heads. Okay? Or we could say A is the event that it rains tomorrow. Okay? So, you know, we can use the letter A. You know, probably a better name is probably rain. Okay, and so and we indicate the probability by sticking it in the parentheses. Okay, so we will say the probability associated with an event is a number. Okay, and it's indicated with P parentheses. Okay, so we'll say parentheses of P heads, so this is the probability associated with the event that the coin lands heads. This is 0.5, or probability of A, maybe 0.2, or probability of rain, 0.2 or something like that, okay? So it's important that, so do not write okay, this is not correct. Do not write this. This is okay, because heads does not equal 0.5. Heads is the event. You only assign numbers to the probability associated with an event, okay? So don't write heads is 0.5 or A is 0.2. You can say probability of A, or the probability of rain, is 0.2, but don't say that the event itself is equal to some number. All right, can I flip to the next slide? Okay, so, so all probabilities will have a value between 0 and 1 inclusive. Okay, so we'll say, for any event A, so any event possible, we can say the probability of A must be less than or equal to 1, and it also must be greater than or equal to 0, okay? And so this is just, this is the shorthand way of saying all probabilities will have a value between 0 and 1 inclusive. Okay. All right. And then we define, so if A is some event, then the complement of A, and this is complement spelled with an E, not a complement with an I, the complement of A is the event, or, is the outcome when A does not happen. Okay, so if, if A it is, it rains tomorrow, then A complement, which can be written a few ways, okay? We can write it AC, or I can just write not A. This means it does not rain tomorrow. Okay, and there's only, this encompasses all possibilities, okay? A together with its complement forms the complete set of possibilities. That's where the word complement comes from. It has the same root as complete. A and its complement AC, or or not A, covers all possible outcomes. Okay? Tomorrow, either it's going to rain at some point during the day, or it doesn't. Okay? There's no other possibility. Okay? Even, either it rains for part of the day, or the whole day, or whatever, or that doesn't happen. Okay? There's no other possible outcome. So A and its complement cover all possible outcomes. All right? And so what this gives us is that the probability of A plus the probability of the complement of A, so I'm just going to write probability of not A equals 1. Okay, because the probabilities of these two things combined equal 1. When the probability is equal to 1, that means surely this is going to happen, okay? And so another way, another thing that we can take from this is that the probability of not A, maybe I'll just slide this over. Oops, that's not what I wanted. The probability of not A is equal to 1 minus the probability of A. Okay, so the probability of it, if the probability that it rains tomorrow is 20% or 0.2, the probability that it doesn't rain would be 0.8, okay, 80%. If there's a 20% chance of rain, that means there's an 80% chance of not rain. Okay. I think, and there's kind of this, there's this notion of probability, and I want to kind of just dispel this, okay? I think there was a meme floating around, and it was like Velociraptor or whatever, okay? I don't know if you guys are familiar with this. And it said, if the weatherman says there's a 50% chance of rain, does that mean he doesn't know if it's going to rain, okay? Or I should say weather forecaster, not, because it could be a woman, right? If the weather forecaster says 50% chance of rain, does that mean he or she does not know if it will rain? Okay, and what's the answer there? No. The answer means yes, the person does not know if it will rain. And that is correct, okay? Yes, the person, does that mean she, yeah, yes. The person does not know if it will rain. Okay, but here's the thing. If the weather forecaster says there's a 99% chance of rain, does that mean he or she does not know it will rain? The answer then is still yes, okay? Even if the person, so if the weather forecaster, same thing, okay? 99% chance of rain. Does not know if it will rain. And the answer there is also yes. The person still does not know if it will rain. And the truth is anytime we're talking about probability, that essentially means there is uncertainty involved. Unless the probability is 1 or the probability is 0, there is uncertainty, and that means we cannot know what is going to happen. This is the idea behind probability. So, the only time you can be certain is if you say the probability is 1 or 100% or the probability is 0%, okay? Meaning it for sure will happen or it will for sure not happen. But at 99% chance of rain, that means there's still a possibility that it doesn't rain. And that means, we cannot predict the future, okay? And, we don't know if it will rain. If someone says there's a 99% chance of rain, and someone says, do you want to bet $1 million that it will, or, would you be willing to, bet your life on that or something, okay? You would say it would be wise to not, right? because there's still a 1% chance that you're wrong, and we cannot predict the future, okay? So as long as the probability is not 0 or 1, the answer is, does that mean he or she doesn't know if it will rain? Exactly, okay? Only for probabilities of 0 or 1 do we know something's going to happen. Yes?
On your previous slide, you had the probability of rain plus the probability of not rain equaling 1.
Yes.
So don't they cancel each other out?
Okay, so if there's a 99% chance of rain, that means there is a 1% chance of not raining. Okay? And so tomorrow there's a 100% chance that it will either rain or not rain. Okay? There's a 100% chance that either it's going to rain or it's not going to rain. Okay? That sounds silly to say, but that's the only thing that we know for certain. Okay? Whether it actually rains or doesn't rain is uncertain to us. Okay? It's probably, we can say it's very unlikely for it to rain, or it's unlikely for whatever to happen, but it's still uncertain. It is still possible. Okay? So in this case, we are only certain if the, quote, probability associated with an event is 0 or 1. Okay. All right, so here we have probabilities for outcomes, or I should say, for events with quote simple outcomes. Okay, so sometimes we have situations where the different outcomes all have an equal probability. Okay, so there are often situations out there, I should say, where the different outcomes have equal probabilities. So for example, okay, flipping a coin, there are two outcomes, heads and tails. And both are equally likely. Okay, or we can roll a die. Okay, 6 outcomes. Okay, and all 6 are equally likely. Okay, or selecting a card from a deck. $52 outcomes, all equally likely. Okay, or selecting a person at random. And I can keep going here, but a person at random from a crowd. Okay? And so however large your crowd is, if you're selecting someone at random, each person has an equal chance of being selected. Okay? Okay, and so in these types of situations, okay, you can have events that kind of combine some of these outcomes together. So for example, we can say, what is the probability that the event, if our event is drawing a card that is a heart from the deck, okay? So, you know, we can have events, okay, made up of, you know, several of these outcomes. Okay, and so we can say, you know, the event is, you know, a random card is a heart. Okay, so we can ask, what is the probability of drawing a card that is a heart? Okay, and so the way we answer this, the probability of these events, is we count the number of events or number of outcomes in the event divided by the number of possible outcomes. Okay, so if you're familiar with playing cards, how many cards in the deck are hearts? 13. There's the ace through king of hearts, okay? So 1 through 10 basically, and then jack, queen, and king. So there's 13 hearts, and in the deck we have a total of 52 cards. So the probability of drawing a heart is 13 out of 52, which simplifies to 1 out of 4, or 0.25. Okay, so the probability of drawing a card that is a heart, 1 out of 4, 13 out of 52, something like that. Okay? Is that all right? Okay. Here we can have, you know, more complicated events, rules. Okay. So we can talk about, there are and rules and or rules. Okay, let me pull up a table from our textbook. This is on page . Okay, so this is a table containing data on whether this is a survey of, I guess, 665 people. Okay, and they asked them, you know, what was the level of education that you, highest level of education that you attained. So, you know, if they didn't finish high school, they would answer less than high school. Or if they completed high school but did not go to college, they would say this. Or, you know, if they completed college or higher education, they would answer this. So they ask, you know, what was your educational attainment? And are you currently single, married, divorced, or widower? Okay, so I guess single is probably never married, I should say. This is okay. So single. I probably need to update the language there, but so single, never married, married, divorced, widower. Okay, so this is the data that we have. All right, so we could ask a few questions. We can say, what is the probability? So our random event will be, I'm going to select one person at random. Okay, so we're going to select a person at random. So how many people total are there? 665, and that means and every single one of these persons have an equal chance of being selected. Okay, so I can ask, what is the probability that a random person, randomly selected person, is married? Okay. All right. And what is our answer there? Okay. So we're going to just use kind of our rule of how many people are included in that outcome divided by how many total possible outcomes are there. So for this one, the number of people that are married is right here. There's 408 people total. Okay, because these are total numbers. I could add up these. So you know the actual data is kind of inside this section of the thing, and then this stuff out here. These are just these are here to help us. Okay, with the totals. Okay. There's 408 people who are married. And we divide by 665. This is total people in the table. Okay. And you know, if you thought maybe you have to add up the entire column and you added up 408 along with these other numbers, you know, then you would get something like 816, okay? And then if you divide by 665, you would end up getting a number bigger than 1, okay? And so that is kind of just one way to know that you've made a mistake. If you ever get an answer that is bigger than 1 or negative, less than 0, you know you've made a mistake, okay? So, you know, so I'll put this, if your answer for a probability question is ever greater than 1 or, you know, less than 0, meaning it's negative, you have made a mistake. Okay, we can ask, what is the probability that someone, you know, is in the college or higher group? Okay, I guess went to college or higher. Okay, and our answer there would be what? 143 divided by 665. Okay, so far so good, because we have a total of 143 people who've finished college or higher. Okay, and then so for and, we just kind of combine our information together. We say, what is the probability that a randomly selected person, that someone is married and went to college. Yeah, so in this case, how many people went to college and are married? Okay, so 98 people out of 665. All right, so far so good? Okay, let's talk about the OR probabilities then. Okay, so we're going to kind of use our same table here, so you don't have to like rewrite it if in your notes. And we can just change the question a little bit, just slightly by saying, what is the probability that someone is married or has a college education or higher? Okay, now in statistics, whenever we use the word or, this means the or is always an and or. It's always a and or, okay? Because in our in the English language, or can be an exclusive or an and or, okay? Because I could say, and it's just, when you're talking to someone, you kind of just pick up on these subtleties of the language. But I could ask you something like, a question like, do you like chocolate or vanilla ice cream? Okay, and probably you would answer me chocolate, or you'd answer me vanilla. Okay, I could ask the exact same, use the exact same words, right? And I could say, do you like chocolate or vanilla ice cream? Okay, and then what would your answer be? Your answer would be yes, right? Or no, okay? And those are the exact same words, but in statistics, whenever we use the or, it's always the second case where it's, do you like chocolate or vanilla ice cream? Meaning, do you like chocolate or vanilla ice cream or both? Okay? And you'd answer me yes or no, okay? We can use the same words and have this exclusive meaning, but in statistics, whenever we use the word or, it's the and or, okay? So what's the probability someone is married or has a college education or both, okay? That's essentially what we're saying here. Okay, how would we answer this?
Would you have 3 different things? Would you have like 3 separate calculations?
Yeah, you'd have to add a whole bunch of numbers together. Okay, so one thing I'm going to say the wrong answer. Okay, the wrong answer is to say, well, we're going to take the probability that someone is married and add the probability that someone has a college education. college or higher. Okay, because in this case, we would do married is 408 over 665 plus college would be 143 over 665, okay? What is the problem here if I did this, okay? Here I would get, if I added these together, I would get 408 plus 143, I would get 551 over 665. This is wrong, okay? What's going on here is let's go through our table, okay? And just we're gonna just look at the kind of the actual data. We're not gonna look at the summary numbers for us, okay? And let's I'm gonna put a red X or a green check if they should be included, okay? So should these 17 people who are single and didn't finish high school be part of this answer here? No, okay? What about these people who are married but didn't finish high school? Yes, they are included, right? Okay. These people? No. These people? No. Okay. These 68? No. These 240? Yes, okay, because they qualify as being married, all right? These are a no, these are a no, and this entire bottom row is a yes, right? Okay, so here, this would be the long way to do it, but we can add up all of these numbers, right? We can do 70 plus 240 plus 27 plus 98 plus 15 plus 3, okay? And so these are the total number of people included, right? So this is a number of outcomes or number of people included in the event. And then we would divide that by what? Divided by 665, right? Total number of people. So, and so if we add up these numbers, we would have 70 plus 240 plus 27 plus 98 plus 15 plus 3. I would get 453. 453 divided by 665, okay? And so that is definitely one way to get the answer, okay? You know, it's a few numbers to add up, but but that will give us the answer. This answer is correct, right? Because this is clearly the number of people that qualify as someone being married or has a college education or higher. Okay. All right. Well, maybe you don't want to answer, have to add up all of these numbers, okay? Okay, another way to do this is we can take these numbers, 408, so we can say, you know, what is the probability that someone is married? Okay, that's 408 plus what is the probability that someone has a college education or higher? Okay, we'll add that probability, which is 143 over 665. Okay, but what's going on is if I take this number 408, 408 is made up of these three numbers, 72, 40, 98. Essentially, when I say 408, I'm taking 70, 240, and 98, and I'm throwing those together there. This number 143 is made up of 27, 98, 15, and 3. I'm taking those four numbers and adding them together here. So what's happened is I've taken this number 98 and I've included it twice, because those 98 people are included in this number of 408, and those 98 people are also included in this number 143. So what I have to do is I have to subtract off that overlapped, and I would subtract off those who are married and college higher. Okay, so I would subtract off 98 over 665. Okay, so they all have a common denominator, so I can add them together. 408 plus 143 minus 98 divided by 665, and I will show you that indeed 408 plus 143 minus 98 gives me 453. okay? So there we go. Is that okay? All right, so maybe just a quick check of your understanding. I'll pose a few questions up here. And then you answer them, and then we'll take a break. Okay, so I'm going to ask, what is the probability of So try and answer these. Take a few minutes. If you're watching on YouTube, I'm going to pause the video here, and when we come back, we'll go over the answers. All right, let's go over our answers here. Okay, so probability. So again, our kind of our guiding principle, at least for this thing, where in this is a situation where we have simple outcomes where everybody has an equal probability of being selected. So just kind of looking at our table here. What is the probability? How many people are in the less than high school and single group here? 17, okay? So the probability is going to be 17 out of 665, okay? So, you could turn this into a percentage if you want, or a decimal, so we would have 0.025256, okay, if I round off to 4 decimal places. Okay, high school or married, okay? So we can break this out as probability of high school plus probability of married. This is just one way to do it, minus probability of high school and married, right? So high school, we have 397 out of 665. Married, we have 408 out of 665, okay? And if you just stopped there, you would have a clear indication that you've done something wrong, because 397 plus 408 is much bigger than 665. It's, 805, okay? And because you're getting a number, 805 divided by 665 is bigger than 1, you know you've done something wrong, okay? And what that thing is that you have to subtract off the overlap of 240 over 665, okay? And so common denominator, you can combine them all. 397 plus 408 minus 240 divided by 665. This gives me, okay, so we'll do this. 397 plus 408 minus 240, 565 over 665. And I get 0.8496. Okay, so far so good? Okay, these last two, you have to think about these. They're, just a tiny bit tricky, okay? Single or divorced, okay? We take this entire column, so we could do probability. So again, single should be written as never married, okay? You know, and then we're assuming that if someone is divorced but then, or got divorced but then got remarried, they would answer the survey as currently married, right? Okay, so this would be probability of single plus probability of divorced, okay? And then we would subtract off probability of single and divorced here, okay? So single would be 112 divided by 665 plus probability divorced, we have 84 divided by 665, okay? And can someone answer the survey and say I belong in this column and this column? No, okay? Yes, it is possible to, I mean, if you are divorced and you haven't remarried, then you are technically still single, but the way this survey is set up, this should be single, never married. So you cannot be, you should not show up twice in the same table here. So there are 0 people that are in both the single and divorced columns, okay? You cannot be in both of those columns. So we just subtract off the 0. So in this case, it's just 112 plus 84 over 665. 196 divided by 665, and we get 0.2947. How do we feel about that? Is that okay? All right, and then so what is the answer to this last one? Probability of married and single. 0, right? There's no person that is going to be in both the married column and at the same time in the single column. Okay, no people in there, so the answer here is 0. Okay, so please make sure you understand all of these questions. Okay. Okay, with that we'll take a 10-minute break.